My name is still Peter, and welcome to my channel Data Engineering in Practice and my second data engineering project demo. Once again, I will try to show you my data solution I've been working on as a response to some business problem. And since my first video was almost 3 hours long, so this time I will do my best to fit into half of this time. And even though in many ways this system is more advanced than the first one. Okay, my second project is called Health Data Lakehouse. Once again, it is an end-to-end cloud-based data solution, but this time it is ELT Data Lakehouse, a platform designed to integrate air quality, environmental, epidemiological, and public health data from multiple public APIs. So comparing to my previous system, this time we have some new data concepts or abstractions like ELT pipeline and Data Lakehouse. Okay, so ELT, it is a modern approach to that data processing, in which first you extract data from data source, but then you load it into the default destination, and then in this destination you conduct some required transformations on data. I will try to explain why I use this approach instead of classical ETL. Well, in business problem and context part of this video. And what is Data Lakehouse? Well, in my opinion, the best way to explain complicated tech concept is to use metaphors. So imagine that the data lake and data warehouse, they fall in love and have a baby, and this baby they call it Data Lakehouse, and it has both parents' features, so like every parent's dream. And what are those features? We will delve into this later. Okay, compared to my first project, this time this one is also more focused on orchestration and infrastructure automation. So I will show you how I deploy infrastructure as code approach with Terraform. I also use what is called Meddalion architecture in this project. So Meddalion architecture is a data design model used to logically organize data process. Well, the idea is to improve data structure and quality step by step as it moves through 3 layers: bronze with raw data, silver with clean data, and gold with business model of business ready data. And this approach was first introduced, I think, by Databricks. Okay, this demo structure is similar to previous one, so I will guide you through the business problem, then some system architecture and implementation, some challenges I had to deal with, and well, finally a data product demo and some conclusions and insights as a sum up. Okay, to make it quick and make this video shorter, let's start. Okay, so business problem and context. In this project, well, I assume that some public health institutions or environmental agencies or different kind of researchers and policymakers need some centralized platform for analyzing relationships between air quality and different health indicators across different European countries. And I choose this topic because air quality is a great big problem in my country of origin, which is Poland, where unfortunately we have one of the worst air qualities in the world in winter. So this is like the topic of this system and of this project. and who can stakeholders be in this scenario? So main stakeholders can be including, but of course not limited. Once again, some analysts, like data analysts, because they analyze data, but also public health or environmental analysts. Who else? Some environmental researchers or scholars. So people who conduct research on different environmental issues or factors. Policymakers, so people who make decisions, public decisions, decisions about environment and decisions about public health, for example. Who else? Some epidemiologists, they can, research well, the connection between air quality, for example, and some epidemiological factors or indicators. Well, main stakeholders can also be some environment or public health non-governmental organizations. And last but not least, some potential machine learning teams. Well, some potential machine learning teams, who wants to create, for example, I don't know, lung diseases prediction model based on, among others, some air quality features. Okay, so these are main stakeholders of this data solution. And what are the main problems and pain points of this current solution, of lack of current solution in this area? Once again, well, we have multiple public data sources now with different data schemas, different data granularities, different update frequencies, and some different formats. This time we're gonna have some semi-structured JSON formats in this solution. Another pain point, once again, well, because we have different APIs and different data sources and different data formats and structures, well, once again, we have to collect and clean and transform data manually, which takes a lot of time. And well, this is not like analysts or machine learning engineers role to do that. More data engineers should prepare system which automatically collect and clean data. What else? Another problem is the combining health and environmental data is not straightforward. We can't combine health indicators and some environmental features straight in this current solution. And that's why some cross-country comparison, for example, within European Union countries, well, now it's very difficult because of both pain points and problems. Okay. Well, based on these problems and based on stakeholders' needs, I gathered some requirements, but this time I didn't divide these requirements into functional and non-functional because it would take additional, I don't know, 20 minutes to talk about functional and non-functional requirements. I just gathered some basic requirements for this platform. Well, this platform should first of all automatically ingest data from multiple public APIs. What else? Well, these solutions should store both raw and processed data sets. Why? Because, well, we can have different analytical use cases. So sometimes analysts or machine learning engineers or data scientists, they need raw data, for example, right? Well, another requirement, this system and this solution should handle semi-structured JSON data and some schema changes. It is not like in this first project when we have CSV files and Excel files. This time data are semi-structured, and we have different JSON types in different APIs. We have like classic JSONs, we have nested JSONs, as you will see in a moment. We have JSON lines, so different schemas, different formats, but basically data are semi-structured. Okay, another requirement. This platform should also provide some reusable data products for different analytical use cases. So not only SQL querying, like in the first, or also BI reporting, like in this first project and system, but also, for example, some future machine learning use cases. Okay. And this system and this platform also should remain scalable and cost efficient for growing data workloads. So, for example, this system should separate storage and computing. Okay, so basically five basic platform requirements. And based on those requirements, I design, as I mentioned before, serverless AWS-based ELT Lakehouse architecture. And now let's stop for a moment, and I will try to explain why I use this ELT and Data Lakehouse approach in this scenario. So, unlike my first project, which used a traditional ETL pipeline and Postgres warehouse, this project works with, first of all, multiple APIs delivering large volumes of semi-structured JSON data with different schemas and granularities. For example, this open air quality platform and API, they aggregates data from thousands of air quality monitoring stations worldwide and process millions of measurements per day. So working with large volumes of semi-structured environmental data makes a cloud-native ELT approach more suitable than some traditional warehouse-centric ETL architecture. So in this scenario, flexibility and scalability became more important, and then loading only fully transformed data. And this architecture, this ELT architecture, is also better suited for modern cloud analytics, where the same data sets can be consumed by different SQL engines, by BI tools, notebooks, machine learning pipelines also, or some data sharing platform. And as a result, this project represents a transition from this traditional ETL warehouse architecture towards some more flexible cloud native ELT Lakehouse approach. Here you can see this beautiful diagram explaining the difference between ETL and ELT approach. You can stop for a moment if you want and check what is the difference between these two approaches, and when to use ETL, when to use ELT, and here and here, and the main takeaways. But to sum up, from my project's perspective, well, basically, ETL was sufficient for project 1 because the goal was structured BR reporting, and this ELT and Lakehouse architecture is a better fit for this project because of that we have semi-structured data in here. We have big data volume and well, different analytical use cases, right? So SQL querying and maybe some future machine learning predictive modeling. That's why, to sum up, I choose this ELT approach. Okay, so now let's see how this system is designed in details. Okay, so system architecture overview. This is once again this system's diagram with all elements and connections between them. Basically, this architecture follows a layered lakehouse approach with Meddalion architecture, so bronze, silver, and gold layer. Okay, but let's start with data sources. I have 4 data sources in this solution for public APIs. First one is open air quality, which provides, in this case, this PM 2.5 indicator or air quality measurement. Second, we have some World Health Organization API, which provides health indicators related to also air pollution, mortality, some environmental health as well. Okay, third, we have this ECDC, so European Center for Disease Prevention and Control API, which provides COVID case data. Used here is in the system as an epidemiological indicator. And fourth, last data source is Eurostat API, which provides some environmental and also socio-economic indicators or statistics. Okay. Well, as I mentioned before, in this project, I focus on European Union countries because the goal was to create a consistent country level analytical well, data set or data tool. Okay, let's go back to architecture diagram. And then after data sources, we have ingestion with, once again, with AWS Lambda, and I have created one function per source. And then we have this Meddalion architecture here. So one S3 bucket, right, for this old project. And inside it, we have 3 prefixes for bronze, silver, and gold layers. Okay, let's see how this S3 bucket looks like. So we have general purpose bucket. This is project 2 Air Health Data Platform bucket, and inside the bucket we have different prefixes. So we have bronze, silver here, and gold here. Of course, we have some additional prefixes over here, like scripts. I put glue jobs scripts here I will tell you later what is that. We have Lambda with Lambda zip archive for each Lambda ingestion deployment. And we have a separate prefix for Athena querying results over here. Okay, so this is like a S3 structure. First, we have this bronze layer over here. And the bronze layer stores raw JSON data exactly as it was received from source APIs. So 4 APIs, 4 different prefixes inside this bronze layer. So partitioning is based on data source. And this layer is important because it's, it preserves source data and makes the pipeline reliable, right? For example, even if transformation logic changes later, I can reprocess the raw files without downloading everything again. So here we have few JSONs, raw JSONs from every data source. It looks like this in this case. Okay. Then we have this silver layer. Okay. And the silver layer contains cleaned and normalized Parquet datasets. Let's check ECDC, for example, and you can see here we have Parquet file here with snappy. And well, basically AWS Glue, as you can see here, AWS Glue jobs read these raw files, JSON files from bronze zone, a layer, parse nested structures, flatten arrays and structs, standardize column names, and write the results as Parquet. And here, and they use Spark actually to do that. So this part is Spark based. As you can see, this part, so ingestion, is Python based, and this gold layer with DBT transformations is SQL based. And so this silver layer contains clean Parquet data sets, right? This is Parquet for ECDC. Let's see, for example, what health organization data, we have Parquet files as well, right over here. And why Parquet? Well, basically Parquet was selected because it is columnar, compressed, and efficient for analytical querying with SQL engine, which is Athena in this case. In general, as you probably know, but it's worth mentioning, there are 2 major approaches to storing tabular data. So we have row-oriented storage, and we can have column-oriented storage. And column-oriented formats like Parquet, instead of storing full rows together, they store values column by column. So, for example, all values from the country column are stored together, all values from, I don't know, year column stored together, and so on. And this approach is much more efficient for analytical and OLAP workloads. Why? Because analytical queries usually read only a subset of columns and process very large numbers of rows. Okay, so ingestion, bronze layer, then some transformations conducted by glue jobs. Then the data stored in a silver layer with Parquet format. And then we have something what is called AWS Glue crawlers and data catalog. And I think it's important to understand what is that. So let's stop for a moment here and explain like basic AWS Glue concepts. Okay. We don't need these API pages anymore. And here we have AWS Glue. Well, in general, Glue is a serverless data integration and engineering service. With Glue, you can create and run full, basically, data pipelines. And key concepts which I use in this project, these are ETL jobs. So let's check, for example, here. ETL jobs, we have 4, I hope, ETL jobs here. Yeah, for every data source we have different job. Let's check, for example, the first one, Eurostat job. Well, Glue jobs, they are like serverless data transformation jobs executed on managed Apache Spark infrastructure provided by Glue. And in this case, their responsibility is to read raw datasets from bronze layer, so JSON data, transform and standardize data, and write process datasets into this silver layer. And we have, of course, code in PySpark over here. And because Glue is serverless, I do not have to provision or manage Spark clusters manually. Okay, so we have scripts, we have job details, we have schedules, and so on. Then another Glue concept is crawlers, and crawlers we have over here. I really hope I have also 4 crawlers here. Yeah, once again, for each data source I have separate crawler. And basically, crawler are automated schema discovery services. Their job is to scan data set stored in S3, not in the database, not in the data warehouse, but in S3, so in a data lake. Infer the structure of the files, detect columns and data types, for example, and automatically register metadata about these files, about this data in Glue data catalog. Okay, and in this project, crawlers scan the silver and gold layers after Glue jobs and DBT. So after Glue jobs and after DBT, transformations finish, and this allows then this query engine, which in this case is Athena, and other AWS services to query datasets without manually defining schemas. So it is like very useful feature. And then we have data catalog. Let's go back to AWS Glue console. We have data catalogs. And what is Glue catalog? It is a centralized metadata repository used by AWS analytical services like Athena. And it stores information about datasets, tables, schemas, partitions, file location in S3, and dataset metadata. Okay, and in this project, the data catalog acts as a metadata layer of this Lakehouse architecture. And then, as I mentioned, Athena used this catalog to understand how datasets are stored in S3 and how they should be queried. Right, so we have 2 databases, AirHealth Gold and AirHealth Silver in this project, and inside these databases, which were created by AWS Glue crawlers, we have tables, for example, right? Okay. So silver and gold datasets are registered as separate databases and tables. And as I mentioned, Athena queries this glue catalog metadata instead of manually reading raw files. So inside this rhelf gold, for example, we have 4 tables for each gold layer table. This is like the most important, so with facts. And as you can see here, we have schema over here, so we have column names, data types, and so on, so on. Okay, let's go back to project architecture and diagram. And let's focus on this part, gold layer and DBT and Athena. So basically this part, this gold layer is built with DBT on Athena as a query engine. Here, silver datasets are transformed into business-ready analytical tables, right? So we have 1 fact and 3 or 2 dimension tables with parquet formats once again, and they are validated and they are registered once again in glue catalog as rhelf gold database, right? Database is rhelf gold, yeah, here. And this transformations between silver layer and gold layer is conducted with DBT on Athena backend. I will show you later this all DBT code, SQL code, and how to use DBT in well, data engineering projects. Okay. So then we have this Athena, and Athena is used. Well, it has 2 functions in this system. Athena is used as a serverless SQL query engine, so it allows users to query gold tables directly from S3 without loading data into some traditional warehouse or database. And this is like one of the key lakehouse concepts in this project. So data still remains in S3 while analytical engines operate on top of it, right? Let's see Athena over here, Amazon Athena. Let's see query editor over here. So this is Amazon Athena query editor, and we have, as you can see here, 2 databases, rhelf silver and rhelf gold, sorry. And for example, inside rhelf gold, we have 4 tables, 1 fact table and 2 dimension tables, and some additional country code mapping table. And in data product demo, I will show you some SQL queries on data stored in S3 gold layer. However, this Athena engine is also the computational backend used for this DBT transformations, and this is important because DBT itself is not a compute engine. DBT generates SQL models and orchestrates SQL transformations, but the actual execution must be performed by an external analytical engine. And in this project, Athena executes SQL queries generated by DBT against datasets registered in glue data catalog. Okay, and what does it mean? It means that DBT defines transformation logic, right? SQL transformations. Glue catalog provides metadata and schemas, right? Schemas in glue catalog for tables. S3 stores the physical data sets over here, for example, for silver layer, and Athena performs the actual SQL computations. And together, these services create an analytical layer of the Lakehouse architecture. Okay. Well, of course, we have some additional features or undercurrents here, like orchestration, like, of course, security, access management, so some governance, some dashboard with pipeline metrics, so monitoring. I'm not going to focus on every aspect of this system. If you are interested, once again, do not hesitate to check my repository or ask questions, for example, at my YouTube channel. I will show you a quick overview of 2 or 3 additional features of this system. First one is orchestration. So this pipeline is orchestrated with AWS step function. This is step function console, and we have state machines here, project orchestration, and you can edit this state machine, and here we have this beautiful diagram of the system orchestration. I have it also workflow of orchestration here in my GitHub repository. It's the same basically. So this workflow runs Lambda ingestion functions. It starts with World Health Organization, then Eurostat, then ECDC, and then open air quality ingestion is split into multiple country groups, as you can see here, 1, 2, 3, and 8, 9 groups. So group of 3 countries, because European Union is 27, so 3 countries per group. And it is executed in parallel, because processing all European Union countries within a single workflow execution initially caused some timeout, of course, and execution time limit issues due to the large volume of API requests and historical measurements. Then, after this ingestions finishes, we have glue jobs. They also run in parallel for different sources. And after we have this success in glue jobs, we have also parallel crawler run with AWS glue once again, and this makes this workflow faster and easier to monitor compared to single monolithic script. So this is basically this workflow, this pipeline orchestration with AWS step functions. Okay, and one additional feature or system over here. Or system undercurrent. Undercurrent is infrastructure as code approach. Probably you can see this is here. Over here there's a Terraform logo. Well, basically I have this Terraform folder over here, right? And in the system, basically Terraform provisions, all cloud infrastructure. So S3 bucket, Lambda functions, glue jobs, crawlers, databases, Athena configuration, step functions, INTF files, right? Event bridge rules, IAM roles and policies, and CloudWatch dashboards, for example, over here. This is a basic major improvement compared to manually created infrastructure, because the environment can be recreated and version controlled, right? I will show you how to use this Terraform, how did I use this Terraform framework in my project later in implementation and engineering challenges part of this video. And last thing to show you, once again, we have GitHub action workflows. Yes. And this time this project includes GitHub action workflows for run tests, for Python unit test, dbt build, YAML file, so workflow for dbt build and tests, and deploy Lambda for Lambda deployment over here. And this introduced some data ops practice in this project. To sum up, code upgrades and changes can be tested automatically before they reach the main branch. Okay, so this was this project architecture overview, and now let's move to some implementation and some engineering challenges. So implementation and engineering challenges. First of all, the repository structure, like in this first project, mirrors the architecture of this platform, separating ingestion, transformation, so glue folder, analytical modeling, so dbt, some orchestration, so Terraform folder, testing, CI/CD, and infrastructure into independent modules. And that makes the project once again easier to maintain and extend. And once again, there's a lot of code to show, so I will briefly cover 4 most important elements of the system. So API ingestion with AWS Lambda, glue transformation jobs for each API, for each data source, and this distributed data processing with PySpark will be covered in more detail in my third project, where I use AWS Elastic MapReduce. Then I will show you some dbt silver gold transformation, so analytical layer over here, and at the end, cloud infrastructure creation with Terraform, so this folder. Okay, so let's start. First, ingestion. Like in the previous project, I have 4 different ingestion scripts for each data source. Let's see, for example, download open air quality Python script. And this open air quality ingestion script is responsible for downloading PM 2.5 data for all European Union countries. And it uses the OpenAQ API and store raw JSON files in bronze layer on S3. And just few important elements of the scripts. So first we have API configuration. So the script defines API endpoints for location, sensors, and yearly sensor measurements. Then we have some API keys and some environmental variables. So the open air quality API key is read from environment variables. It is not hard coded, so over here. Then next part of the code we have EU country lists, so it's a Python list. and the script iterates over all 27 country codes. And then we have to establish some bot-free client to communicate with S3. Then this part, this function, it's a retry logic. So the getJSON function handles temporary API errors and rate limits using exponential backup and some jitter. So it's this line of this code. Then this big function over here. Well, this is sensor selection logic. Since there's thousands of sensor in each country, so for each country, the script searches for the best PM 2.5 sensor based on observed measurement coverage. So this function. Then we have function which returns an annual average for a sensor from days endpoints. And then we have this main function, so Lambda handler. Yeah, and here we have incremental like skip logic. Right, before downloading data for the country, the script checks whether JSON files already exist in S3, and if data already exists, it skips that country. So quite useful feature. And then at the end we have some S3 writes. So raw JSON is saved under the bronze prefix, and it's grouped by country. So quick brief of this Lambda function, and this design makes ingestion modular once again and more robust against some potential API failures. Okay, now let's see glue jobs. So we have 4 glue jobs for each row data source. Let's see once again, open air quality job, script. And this OpenArrayQ glue job transforms raw bronze JSON data into structure silver data set. Okay, so some library imports first, then we have some initialization over here. So this code initializes the AWS Glue runtime environment, including Spark session, Glue context, and the job itself before the data processing begins. Then we have some input and output paths. Yeah, so for input is bronze layer and output is a silver layer in S3 bucket. Then this line of the code, the job reads all raw JSON files recursively from the bronze path, so 1 per country. Then this part of the code over here, we have some schema definition. So this part of the script defines nested schema matching the OpenArrayQuality API response. Yeah, and then this part of the code, very important part. Well, this part of the code parses JSON text using from JSON over here. function. And this line parses the raw JSON stored as text into a structured Spark data frame. And the from JSON function uses a predefined schema. So this one to tell Spark how to interpret the nested JSON structure. So instead of working with plain text, the following transformation can access individual fields, arrays, or nested objects effectively. So to sum up, some Spark deserialize and parse this JSON documents. Yeah, and then over here the yearly array is exploded. So each yearly record becomes a separate row. And then in this part of this script, the job selects and flattens fields such as country code, sensor ID, parameter name, some statistics like average value, minimum and maximum values, median, standard deviation, and so on. And finally, the transformed data set over here is written as Parquet to the silver layer in S3. And to sum up, this is a typical bronze to silver transformation. So raw nested JSON becomes a clean tabular data set optimized for some future analytical querying. Okay, now let's move to some analytical transformations between silver and gold layer with this DBT. Okay, so DBT is one of the core components of the gold analytical layer in this project. And its responsibility is not only transforming silver datasets into business-ready analytical tables, but also organizing SQL logic, managing some dependencies between models, supporting reusable transformations, and improving maintainability of the analytical layer. And before I jump into gold models themselves, I would like to briefly explain several important DBT components used in this project. So DBT project YAML file, these profiles, YAML file, some macros, and some seeds I use in this project. Let's start with DBT project YAML file. Simple file. And this DBT project YAML file is the main configuration file of every DBT project. Basically, it defines project metadata, folder structure, model configuration, some default materialization strategy, and some general project behavior. And in this particular project over here, well, model path, for example, defines where SQL models are stored. So in models folder, here and here. Macro paths defines where reusable Jinja macros are stored. In macros folder, so here. Seed paths defines where the static CSV reference datasets are located, so in seeds folder, and target path defines where DBT stores compiled SQL artifacts. Okay. Then we have profiles YAML file. this one. And this profiles YAML file defines how dbt connects to the underlying analytical engine. And this is very important because dbt itself, as I mentioned before, is not a compute engine. And dbt generates SQL transformations, but the queries must be executed by some other system of framework or SQL engine. And in this project, Athena acts as the SQL execution backend for dbt. Here and here we have Athena. And okay, the profile configuration defines Athena as a database type, glue catalog as a metadata catalog. So here, the target schema, AirHealth Gold over here, some S3 locations for query results and gold data sets over here, and some AWS region, so EU Central 1 for me, some Athena workgroups over here, and some authentication settings. And as you can see here, the project contains two environments, local and CI. And the local profile uses a local AWS profile. Yeah, AWS profile default. And while this CI profile uses GitHub Action, GitHub secrets passed as environment variables. So over here, and this allows the same dbt project to work both locally with this environment and inside GitHub Actions CI/CD workflow, yeah, which I define over here in GitHub Action folder. Okay, next thing I would like to show you are macros. And this is like another important dbt feature used in this project. Basically, macros are macros, so some reusable Jinja-based functions that allow me to avoid repeating SQL logic across multiple models. No, to instead of duplicating the same SQL transformations many times, the logic can be centralized inside reusable components. And I use two macros in this project. First one is for country code mapping, and this macro converts two-letter ICO country codes into three-letter country codes. And this was necessary because different APIs use different country code standards. For example, Open Quality use two-letter codes, and while WHO and ECDC use three-letter codes. So instead of duplicating mapping logic across multiple models, the transformation is centralized inside one reusable macro called country macros SQL file. And another macro calculates percentage change. So over here, it's a simple case when SQL statement. And this macro standardizes percentage calculations and prevents repeated case logic inside analytical SQL models. Okay, next thing is dbt seeds over here, and I have just one simple seed over here. Basically, dbt seeds are static reference datasets stored as CSV files and automatically loaded into the analytical environment by dbt. And in this project, I use a seed called country code map CSV file. Let's see it. a simple CSV file, and this data set contains mapping between 2-letter ICO country codes and 3-letter country codes. Yeah, as you can see over here. Okay, now let's move to DBT models. Gold models. Basically, what is a DBT model? Well, it's quite simple. It's a single SQL file containing some select statement for data cleaning and some transformations. And in my project, the most important model is fact health. So fact table creating over here. And what this model does, well, in brief, first it pivots WHO data over here. Why? Because HW indicators are originally stored as rows with indicator code, and this DBT model converts selected indicators into separate measure columns. Then it aggregates ECDC data over here. So weekly COVID records are aggregated to annual country level counts. Third transformation over here. Well, this code aggregates open air quality data. PM 2.5 measurements aggregated to, once again, country year level as average PM 2.5 concentration. And then finally, over here, the model joins these data sets with dim country and dimension year. Yeah, these are some joins, and we can see these 2-dimension tables. So let's start with dim country, simple dimension model. In this model, I use, for example, window function here to assign a unique sequential integer to every row, starting at 1. And the rows are stored based on their country code, as you can see here. And then and the resulting number is given in the column alias country ID. Right. And then we have one last model, dim year, over here. And in this model, I use several CTEs, so common table expressions, to make SQL logic more readable and modular. So first, over here, I extract unique years from WHO dataset. Then over here, unique years from open air quality dataset, and finally I combine them into one standardized year dimension. And after that, at the end over here, I use the row number window function to generate a sequential surrogate key, so year ID, and create a decade label over here. Column which simplifies long-term trend analysis, for example. Yeah. And the output is a white analytical fact table with one row per country and year. Yeah. Okay. And one last thing about DBT. These are DBT tests and documentation. As you can hear, here is some schema YAML file over here. So DBT in this project is used not only for SQL transformation, but also for analytical testing, metadata management, and some automatic documentation generation. So this file, this schema YAML file, defines model description, for example, over here, some column descriptions of different columns, like country ID, year ID, some tests for each column, for example, here and here, some relationship between tables, and some analytical metadata for this gold layer. And as I mentioned, this schema YAML file also defines data quality tests, right? For example, primary keys in dimension must be unique and not null, because here I have definitions for not only for this fact error health model, but also for two other models, so dim country and dim year. And we have tests here, so unique and not null. The same here for column ID, for columns, for example, country ID or year ID, once again, unique and not null. Yeah. And what else? Well, additionally, when it comes to testing, this project includes some custom SQL test validating country code consistency, and it's here in dbt in test folder. Some problems, yeah, that's now it's okay. So one custom test created by me. This test basically verifies whether country code follow valid ICO style uppercase formatting. So some simple test. And to sum up, testing in dbt and dbt, well, together these tests help detect, for example, broken joins, or duplicate dimension records, or invalid country identifiers, or some incomplete analytical data sets. Okay, I think it's enough about dbt. So it's basically very useful framework for SQL transformations. Now let's move to Terraform folder, and I will show you how did I create well, this infrastructure, this cloud infrastructure as code with Terraform. Well, Terraform is used to define and provision cloud infrastructure in this project. And before explaining one individual Terraform module, I would like to briefly explain how the Terraform project itself is organized. Well, basically, Terraform infrastructure is divided into multiple TF files, as you can see over here in this Terraform folder, where each file is responsible for a specific part of the cloud infrastructure. For example, this provider TF file defines the cloud provider and required Terraform versioning over here. Then we have variables TF file over here. Well, this file helps avoid, defines reusable input variables used across the project. And this file helps avoid hard coding configuration values directly inside infrastructure definitions. So we have variables like AWS region, S3 bucket name, default tags, some Lambda function variables, some environment specific settings. So these values can be managed centrally and reused across different modules. So basically variable definitions. And there's also a file called Terraform tf-vars, and it stores actual values of these defined variables. Of course, you can't store this file in GitHub repository and show it to the public. So you need to remember to put this file to git ignore. Well, it's somewhere over here. Then we have outputs tf file over here. And this output tf file defines useful output values displayed after deployment, so after Terraform apply. And it's used to expose important infrastructure information after as I said, deployment, for example, bucket name, ARN, so Amazon resource name. Yeah. Some IAM role names or step function are identities. So this is output tf file. And then we have infrastructure definition for each service. For example, S3 tf file. It creates S3 data lake bucket, blocks public access, for example, and enables versioning. We have Lambda tf file. Here it defines ingestion Lambda function using this for each pattern. And for example, glue tf file over here, and it defines glue database, glue jobs, and glue crawlers. Glue jobs over here, jobs, and some crawlers over here. Yeah. Okay, and now let's just briefly quickly analyze one sample Terraform module from this project. For example, Athena, it's quite simple. Athena tf file, and this file is responsible for provisioning an AWS Athena work group. Yeah, AWS Athena work group. Basically, this part, this block creates a dedicated Athena work group called project to Athena work group, as you can see here. Basically, Athena work groups are used to organize and manage analytical query execution. They help separate workloads, control query settings, monitor usage, and manage costs, for example. Then this block of code basically Athena stores query results in Amazon S3. So this configuration defines where query output should be written. And as you can see here, instead of hard coding the bucket name, the configuration uses this Terraform variable I just showed you a moment ago. Then we have these two settings, two parameters. First one is enforce workgroup configuration set to true, and this setting forces all Athena queries executed inside this work group to use the defined work group configuration. And then this another second setting, set to true, publish CloudWatch metrics enable. Well, as you probably guess, this enables CloudWatch metrics for Athena work group. Yeah, and as a result, this project can monitor, for example, query execution statistics, query failures, and data volumes, and overall Athena usage. And it improves, for example, of observability of this analytical layer. And then we have description, Athena workgroup for querying glue, data, catalog, silver, and gold. So finally, the model includes a description, explaining the role of this work group within the architecture. And as you can see, in this project, Athena queries datasets registered in glue data catalogs from both silver and gold layer. And this Terraform module is relatively small, but it demonstrates several important infrastructure as code concepts. For example, modular infrastructure definition, some reusable variables, some centralized configuration, observability, and some reproducible cloud resources provisioning. Okay, to sum up, this approach makes the infrastructure easier to manage and reproducible, because instead of clicking through AWS console all the time, infrastructure is described as code and is stored in Git. Yeah, so we can conduct versioning on it, for example. Okay, that's enough about the code in this system. Now let's just check one last thing. So some engineering challenges I had to deal with. And well, one last thing before I show you final data product of this system. So some engineering challenges I had to deal with. There was a lot of different engineering challenges in this project. I just named four, in my opinion, most important, four of them. First challenge was nested JSON files processing. So basically, raw API responses were not analytics ready, and the solution was to use glue jobs, which I show you one of glue job with PySpark to parse, to explode and flatten nested JSON structure into Parquet tabular Parquet datasets. Next challenge was different temporal granularities, and the source do not use the same time granularity, for example, and for example, open air quality is based on sensor measurements aggregated yearly. World Health Organization indicators are also yearly, but ECDC data is weekly and had to be aggregated to annual level, and basically the gold layer standardized this into country, year, grain. Okay, third challenge, orchestration complexity. This ELT pipeline contains multiple dependent steps, and the solution was to use step function, AWS step function, to coordinate Lambda ingestion, glue transformation jobs, and glue crawlers. And well, parallel execution was used where it was possible. And one last challenge in this project was dbt and Athena configuration. Well, basically running dbt on Athena backend requires careful configuration of catalog, database, S3 staging directory, glue data catalog, some external table materialization. So a lot of different well, configuration to manage. So this was main engineering challenges. And now let's dive into the data product demo. Okay, so I'm in AWS Athena query editor, and in this project, the final products, data products, are reusable analytical data sets stored in S3, cataloged via glue, and exposed through AWS Athena. And this is important because the project is designed as a data platform more, not only maybe as a reporting solution. And so data analysts or data scientists can use both raw or cleaned or business-ready data for different use cases. We have to change database for AirHealth Gold if you want to conduct some queries on this Gold business layer. And as you can see here, the Gold layer contains 2-dimension tables and 1 fact table, and this additional country code map. Okay, and I will show you just 2 simple queries through Athena just to prove that the data inside this system and this system is actually working. And I'm not going to analyze the query results. No, this is not the purpose of this video. Okay, so first, just very simple query. Let's just check if there are data inside this fact AirHealth table. So select all from fact AirHealth, exactly, and let's just limit the results to 10 because well, the more data you query in Athena, the more money you have to pay for it. Let's run this simple query. Okay, so as you can see here, this query shows the final integrated fact table. So each row represents 1 country and 1 year, right? 1 year and 1 country. Here we have some country ID, year ID, so some keys. And here we have some different environmental or health indicators. We have some null values as well. Okay, we can check other 2 dimension tables. So dim country. Let's check if we have data inside it. Yes, we have country ID, country code, and so on, country name, but also average population of each country. And let's just check last dimension table, so year. Once again, we have year ID, year, and decade label. Okay, so to sum up, there are some data inside these tables. And let's just create one last query. let's join some this fact table and this dimension tables to check if well, the star schema works. Okay, so let's select from fact health. Let's alias it as F. Sorry. And let's join it with in country as C on F country ID equals C country ID, and let's join another dimension table, dim year as Y on F year ID equals Y year ID, right? Okay. And let's select, for example, country name and maybe year from this dim year table, and some indicators from fact table. Let's check what do we have here. For example, let's have average PM 2.5 concentration. Yeah. Okay. Let's select one indicator from World Health Organization. So WHO. I don't know. Let's check. For example, WHO R 62 42 value. And maybe one last thing from this. So maybe ECDC annual COVID cases. Yeah. And one last thing, let's order by, well, first country name and then some year. Okay, and maybe let's limit to 30. Okay, let's check if it's working. Yeah, it's working. So we have some country name, year, and some indicators over here. We have some null values, of course, but sometimes, like in this EDCD annual COVID cases, it's obvious because, you know, pandemic was from 2020 till 2023 only, so 4 values here. I'm not going to analyze the results. I just wanted to show you that star schema works. And it does, of course, depending on use case. I can use also raw or clean data if I want, or instead of analyzing raw files, users can query clean business ready tables, like over here. you can also in Athena save this query, and query results we have over here, but we can also find them in S3, for example. And to check what are those indicators, we can check my repository. Over here, project 2. And here in documents, I have sources markdown file. And for example, this World Health Organization R42 value, so indicator, it is, what is that? Ambient air pollution attribute death rate per to 100,000 people, age standardized. Okay. And as you can see here in this projects bucket, this query, Athena query results are stored also over here as CSV files, for example. Okay. So now let's summarize this project. Okay, so to sum up, this project allowed me to design and implement a complete AWS-based ELT Lakehouse platform. And this system covers API, ingestion, raw data, storage, bronze, silver, and gold architecture, so Meddalion architecture, glue transformations or jobs, and glue crawlers, and glue catalog metadata management, Athena querying, dbt modeling and testing, step function orchestration, CloudWatch monitoring, Terraform infrastructure, and GitHub Actions CI/CD workflows. And basically the three most important lessons learned for me personally from this project. First one is that well, Lakehouse architecture is useful when data should remain flexible and reusable. You know, instead of loading everything into the traditional database, the system stores data in S3 in this case, and exposes it through Athena and Glue catalog. And this solution supports scalable storage of semi-structured data with JSON format, serverless querying, so separates storage and computing, and the system features can be scaled separately, so storage and computing can be scaled separately, and well, this system also supports some future integration with other tools or frameworks like machine learning frameworks. Okay, so another takeaway or lesson learned for me is that dbt data build tool brings structure and analytical transformations. So dbt makes SQL transformations more modular, testable, documented, and easier to maintain. And it also provides lineage tests and clear separation between source data, so raw data, and business-ready models. Okay, and last lesson learned for me from this project is that infrastructure as code approach is essential for production-oriented cloud projects. So Terraform makes the architecture deployment, well, first of all, automated. So instead of manually clicking through web console, I write declarative configuration files, these TF files, and then with a simple execution command, Terraform automatically provisions, updates, or tears down entire infrastructure. Additionally, this Terraform makes architecture deployment more reproducible. So Terraform uses state files to map out infrastructure, and this means I can deploy the exact same environment effortlessly, which completely eliminates something like configuration drift or a human error, my error. And with Terraform, deployment is also version controlled. So because infrastructure is defined as a plain text files, I can store them in GitHub. And this allows me to track every change, review code via pull requests, roll back to previous versions, and collaborate across teams in the future. So to sum up, this infrastructure as code and Terraform, it reduces manual configuration and makes the project closer to real-world engineering standards. Okay, that's enough about lesson learned, but I'm also, at the same time, I'm also aware of some limitation of this system and this solution. First limitation is that this gold layer in my system is, well, simplified. The analytical model focuses mainly on country year analysis, while some ingested dataset, for example, this Eurostat dataset, are not yet fully integrated into the final gold fact table. And the current gold model is simplified and focused mainly on current country, year analysis. Okay. Next limitation is, well, I'm also aware that this architecture still represents a simplified Lakehouse implementation rather than fully mature enterprise grade data lakehouse platform. For example, the project stores analytical data sets as packets, as you could see on S3. Well, but it does not yet use advanced table formats such as Apache Iceberg or Delta Lake or Apache Hudi. So as a result, the platform currently lacks some advanced lakehouse capabilities such as ACID transformations, time travel, snapshot versioning, some advanced schema evolution, and optimize incremental processing. Okay. Third limitation is limited data quality framework. Basically, data quality is currently based on DBT tests in this solution, schema validation, and some ingestion level checks rather than dedicated validation frameworks and quality gates. I'm aware of that. And more production orientated platform would additionally include some dedicated data validation framework like Great Expectations, some automated quality gates, some anomaly detection, and some alerting mechanisms. Okay, and I'm also aware that this system can be developed. So in the future, this platform could be extended with more health indicators, more granularity, so regional level data, for example, some incremental processing, some strong data quality checks, and some different kind of publications like AWS Data Exchange, for example. And of course, some machine learning projects, for example, respiratory diseases prediction, risk prediction based on air quality, and some socio-economic indicators, right? And as you can see on this presentation, these advanced Lakehouse features are not deployed yet, because in my third project, I use Apache Iceberg as a data storage format. So these are areas I started exploring more deeply in my next project. Okay, thank you for watching. I would be happy to discuss architectural decisions once again, some trade-offs and possible improvements of this solution. And I will be more than happy if you see my third data engineering project demo, data platform for recommendatory system, in which I introduce Apache Iceberg tables as a part of a more advanced Lakehouse architecture. So thanks again for watching.